Lev Horodyskyj, PhD, from USA. Dr. Lev Horodyskyj completed his PhD in geoscience and astrobiology at Pennsylvania State University. Between 2010 and 2018, he worked at Arizona State University developing innovative digital science lab courses using intelligent tutoring system, including the astrobiology-focused habitable worlds. The course won wide acclaim from both students, instructors, and formed the basis of successful grant from the National Science Foundation and the Bill and Melinda Gates Foundation. And now, Dr. Lev will bring the topic climate change, science, and economics. Let's welcome our fifth speaker, Dr. Lev Horodyskyj. The time is yours.
All right, thank you. Can you see my presentation and can you hear me?
Yes, I can see clear.
All right, excellent. Okay, so I'll be talking about climate change, and I'll be talking mostly about the science and its impact on economics. Just to give you a brief overview of who I am, as Dr. Prince Charles introduced me, I have a PhD from Pennsylvania State University in geosciences and astrobiology, and I've spent a lot of time working on digital education, particularly in the sciences, including new programs that I'm doing through my nonprofit. So I was quite interested earlier on when we were discussing how we deal with digital technologies when we have to do a lot of remote learning. I was in Indonesia for a couple of months on a Fulbright scholar program, but I had to leave early because of the crisis. So that's how I ended up getting involved in this conference. And I'll be focusing mostly on the science of climate change and the geosciences and my astrobiology background, which is a combination of sciences of astronomy, geology, and biology to answer the question of, is there life elsewhere in the universe? It gives me a lot of cross-disciplinary experience, so it allows me to make connections across a lot of fields. So just to give you a brief orientation of, this is the US. I've labeled where I'm from, Arizona. That's home. It's this nice brown splotch here in the lower left corner. After I returned from Indonesia, I spent time in quarantine in the Michigan area, and I'm currently in Virginia. And I'll be headed back to the tropics to an island in a couple of weeks for a new position. What's interesting as you look here is that you see differences in coloration, the brown versus the green. And when you expand to the rest of the world, you start to see certain patterns that you can, that repeat. So for example, you can see this tropical band right here where everything's green. You have the Indonesian rainforests and tropical conditions there, as well as the jungles of Africa and the Amazon. But if you move farther north and further south, you start getting into these desert bands. And that's where I typically live. I live in one of these desert bands where it's quite dry, and you can see that there's a lot of brown along this stripe. Then if you move farther north and south, it gets green again. So you get our temperate climates. And then when we move towards the poles, we get to more deserts because the poles are essentially deserts. Most of the rain and most of the snow falls along the coast, and not quite in the center. So these are the patterns that we want to explain. So coming from this astrobiology perspective, I like to think of global perspectives. Earth is a sphere, and that sphere is impacted by sunlight. And that sunlight is unevenly distributed across the planet's surface. You can see that you have high concentration of sunlight where the planet is directly facing the sun, and you get less sunlight along the North Pole and South Pole where the sun is hitting the Earth at more oblique angles. This results in a temperature differential where you have hot temperatures in the equator and cold temperatures along at both poles. And typically in nature, when you have this kind of discontinuity in temperatures, you establish a gradient. And what nature is very good at doing is dissipating gradients. And in order to do that, you need to move energy from the equator to the poles. This is typically done by the atmosphere. You'll have hot, warm air rising in the poles. This will cause the air to cool and the water vapor in the air to condense. So you get a lot of rain in these bands. And then that air makes its way eventually to the poles. So you could take this warm air and distribute it to the poles where it's colder to try to even out that temperature difference. That air cools and sinks, and then it moves along the surface of the Earth back to the poles, and so it circulates this way. So this is basically a giant convection pattern. You see similar things when you're boiling soup. You see these convection patterns. It's a quicker way for heat to get redistributed within your pot of soup. What we see in reality on Earth is we see three convection patterns. We see two of these temperature-dependent ones. One's close to the pole, one close to the equator, and then you have this other circulation between where the air is getting tumbled between these two convecting cells. And these are called the Hadley cells, the Ferrel cells, and polar cell. And so you get these wind patterns that you see across the entire planet. And that's why we have our tropics, our intertropical convergence zone, the trade winds, the westerlies, and the polar wind currents. So this is basically Earth's way of redistributing energy across Earth's surface because it receives energy unevenly. So that helps us explain these vegetation patterns that we see, vegetation and precipitation patterns that we see on Earth's surface. And of course, not everything follows this pattern. You have areas of dryness where it should be a wet and areas of wetness where it should be dry. This can be caused by topographic features like mountains. You can get rain shadow effects where mountains push air up, causing it to cool and rain out. So that's typically what happens in India. And then you get places off the coast where places like Florida, which should be in the dry region, end up very wet because they have a lot of water surrounding them. Energy is also redistributed via ocean circulation. So this is basically the giant conveyor belt that drives all ocean circulation on Earth. And it is driven both by this temperature gradient and also by changes in salinity. And so both of these patterns act to redistribute energy across the surface of Earth, and they're very important because what they do is they create climate. And that's not the only thing that determines the climate. This is what's known as the greenhouse effect. Without any kind of atmosphere, Earth would be too cold for liquid water based on basic physics calculations. But we have an atmosphere, and the atmosphere bottles in some of the heat. So basically, sunlight that comes in through the atmosphere, the Earth's gases are transparent to incoming radiation, which is why you can see me and I can see you as we're chatting right now. But as Earth absorbs this energy, it heats up and it emits in the infrared, kind of like your stovetop or an oven that's emitting heat that you can't see but you can feel. And gases in Earth's atmosphere do interact with this transformed sunlight. So it's no longer visible light, it's now infrared light. And gases interact with that and keep it from escaping the space, raising Earth's temperature and keeping it habitable so that we can actually live on it. The four major greenhouse gases on Earth are water vapor, which is the most important one and the most abundant one, methane, carbon dioxide, and nitrous oxide. When we talk about climate change, we typically focus on carbon dioxide because it's the only one that's regulated on very long timescales. Water vapor is regulated by temperature. So, and water vapor concentration, if water vapor concentration is too high, it rains. Methane and nitrous oxide are reacted away by oxygen on scales of 10 to 100 years. Carbon dioxide, the only way to remove it from the atmosphere is to transform it via soil weathering and limestone precipitation and seashell precipitation in the ocean. And that takes several hundreds of thousands of years. So it is very difficult to regulate carbon dioxide in Earth's atmosphere on a short time scale. So the reason, as I mentioned before, the reason we care about all these patterns is because they determine which places are dry, which places are wet. And the reason we care about that from a human perspective is because it's important for food generation. So for crops and for coral reefs, where we do our fishing and we grow our crops and feed our people. So, so I'm starting at the bottom with natural resources. You end up with lots of different natural resources all over the Earth, and their concentration and their abundance is dependent on various regional variations. And from here, we can build up our civilizational structure. Because natural resources are not evenly distributed, some places will have more, some places will have less, and it won't be the same from region to region. So from there, you start developing economics, or how do we value the worth of these natural resources, and how do we exchange them in a fair way, so that places that don't have a lot of resources can get them, and places that have a lot of resources can sell them and get ones that they need. Of course, when you have economics, not everyone's going to agree on how all of this needs to be redistributed, how it should be redistributed, how it should be charged, how these systems can work. And so that results in a lot of disagreements, or basically politics. And once you start getting politics, you have discussions and elections or dictatorships in certain places. And those politics determine the laws of the land that govern all the lower tiers of civilization. So laws then determine how politics can work, whether certain parties are banned or not, or how parties can politic or not. And they also determine what kind of economic systems and how they will work, how taxation will work. And they can even determine which natural resources are getting exploited or not. And that all has downstream and upstream effects. So it's a complex system that operates. So when we introduce climate change into the mix, our power generation, especially fossil fuels, creates a lot of carbon dioxide. And carbon dioxide is one of those greenhouse gases that isn't easy to remove from the atmosphere. And so what carbon dioxide will do is it will warm up the atmosphere. And because our atmospheric circulation, which determines our climate, is determined by that temperature gradient, when you start between the poles and the equator, when you start changing that temperature gradient, you start changing this whole global air and water circulation. Much like if you turn up the heat under your soup, you'll start changing its boiling patterns and its convection patterns. So climate change impacts our atmospheric circulation, so where it rains and where it doesn't rain. It also changes the strength of a lot of these ocean currents and how strong they are, and whether they're bringing up nutrients from the ocean floor or not. So that determines where your fisheries are going to be. So what you can do during this process is you could take a climate pattern that looks like this and perhaps change it to something like this. And in the process of change, it ends up going very chaotic. So you get a lot more climate extremes during this transition process. And of course, that means certain places that were getting a lot of rain are no longer getting any rain, and places that are getting a lot of rain, aren't getting rain, are now getting a whole lot more rain. And so that disrupts your agriculture, your fishing production, and basically the foundations on which we've built our civilization. So when you start changing the distribution of natural resources and the predictability of our harvests, that has subsequent impacts on economics, on politics, and eventually on law. To get specific about what impacts we could expect in Indonesia for climate change, the three main ones are basically sea level rise, variable weather, and increased ocean temperatures. So sea level rise is probably the one we talk about the most, and the impacts that sea level rise will have, as all as these glaciers and ice caps melt, is we'll lose arable land as it's submerged under the ocean. But we also get loss of additional arable land that's farther away from the coast through cropland salinization. So as the sea level rises, salt water starts to intrude into the groundwater, and so even before the land is submerged under the ocean, the cropland becomes unusable because there's too much salt water in the land. You also end up with more variable weather, which results in more floods, droughts, and crop failures. And you also increase your ocean temperatures that could result in coral reef ecosystem death, including the death of the coral reef and all the fish that aggregate there. So this has enormous consequences for food security, water availability, and disasters. Yep, 2 minutes?
Okay, 2 minutes more.
Yep, I got a timer on. Okay, so the way we try to deal with a lot of these changes is we try to educate the public on climate change and what it is through boring presentations like the one I'm doing now. The problem is that this is predicated on this idea that if I just give you more scientific knowledge, you'll make better decisions. But some political studies here in the US have shown that that's not the case. So in the US, we have the right-wing Republicans and the left-wing Democrats. And what we find is the more science content knowledge we give them, the more partisan they become in their ideas about climate change. So it turns out just giving people more information doesn't actually help them make better decisions, because they pick and choose which information they want to believe and work with. So they'll use the scientific thinking to preferentially throw out ideas that they don't like. So the key to actually getting rid of this partisanship when we're dealing with climate change is to actually improve science curiosity. People who are more curious about their world and are more willing to find contradictory information are ones that tend to make better decisions that are more aligned with reality. So teaching curiosity is very different from teaching facts. So that's what I've been working on in the past few years, doing these game-like and interactive classes and simulations. And I'm currently working on a few projects in Indonesia to work on environmental and climate literacy, with the idea that if we can work with students early on, we can help them make transformational change within their communities that can have downstream impacts on environmental issues that are coming up right behind the COVID crisis. So thank you very much for your time. Terima kasih. That is my email address if you want to get in contact and see some of the digital education projects I'm working on. The website is sciencevoices.org, and I have other type of teaching content on my other website. Thank you.